Electric potential and potential energy due to point. We will begin by discussing the outline for this topic. First, we will cover the potential difference in a point charge field, followed by the electric potential of a single point charge. Then, we will look at the superposition principle for multiple charges. After that, we will explore the electric potential energy of particle systems. Finally, we will go through some numerical examples and discuss conservative fields. To find the potential difference between 2 points, A and B, we start with the general expression. The potential difference, V sub B minus V sub A, is the negative integral from A to B of the electric field vector dot the differential displacement vector ds. For a point charge q, the electric field is the Coulomb constant k sub e times q divided by r squared, directed radially outward. When we take the dot product of the electric field and ds, it simplifies to k sub e times q over r squared times the radial distance dr. This happens because the component of ds along the radial direction is simply equal to dr. By integrating our previous expression from radius a to radius b, we find the potential difference. The result is that v sub b minus v sub a equals the Coulomb constant k sub e times the charge q multiplied by the quantity of 1 divided by r sub b minus 1 divided by r sub a. A key insight here is that this integral is entirely independent of the path taken between the 2 points. This tells us that the electric field of a fixed point charge is a conservative field. The potential difference depends only on the initial and final radial coordinates. By convention, we choose our reference point for zero electric potential to be at an infinite distance away. With this assumption, the electric potential, V, at any distance r from a point charge q is simply equal to the Coulomb constant k sub e times the charge q divided by the distance r. Be careful not to confuse this with the electric field magnitude. The electric potential is proportional to 1 over the distance r, whereas the electric field magnitude is proportional to 1 over r squared. Remember that the electric field is a vector related to force, while the electric potential is a scalar quantity related to potential energy. When dealing with multiple point charges, we use the superposition principle. The total electric potential at a specific point is simply the algebraic sum of the individual potentials created by each individual charge. Because electric potentials are scalar quantities, you do not need to perform complex vector addition. You calculate the total potential by summing the terms for each charge divided by its distance to the point and multiplying by the Coulomb constant. It is very important to include the algebraic sign of each charge in your calculation, because positive charges create positive potentials and negative charges create negative potentials. Now let us discuss electric potential energy. The potential energy is the work done by an external agent to bring charges together from an infinite distance apart. For a system of 2 charges, the work done equals the second charge multiplied by the change in potential. This gives us the potential energy of the pair, which is the Coulomb constant times the product of the 2 charges, divided by the separation distance r sub 1, 2. A positive potential energy means the charges repel each other, while a negative potential energy indicates an attractive force between the charges. If a system contains more than 2 charges, the total electric potential energy is the sum of the potential energies for every possible pair of charges in the system. For example, with 3 charges, you calculate the energy for the pair of charge 1 and 2, then the pair of charge 1 and 3, and finally the pair of charge 2 and 3. You then add these 3 terms together, multiplying the entire sum by the Coulomb constant. This sum represents the total work required by an external agent to assemble the entire configuration of charges from infinity. Let us look at a numerical example. we have a positive 2 microcoulomb charge at the origin and a negative 6 microcoulomb charge on the y-axis at 3 meters. We want to find the total electric potential at point P, located on the x-axis at 4 meters. First, we determine the distances. The distance to the first charge is 4 meters, and the distance to the second charge is 5 meters, which we find using the Pythagorean theorem. Applying the superposition principle, we add the potential from each charge. By plugging in the charge values, distances, and the Coulomb constant, we find the total potential at point P is negative 6.29 times 10 to the third volts. In the second part of this example, we want to find the change in electric potential energy when a third charge of positive 3 microcoulombs moves from infinity to point P. The change in potential energy is simply this third charge multiplied by the potential at point P that we just calculated. Multiplying 3 microcoulombs by negative 6.29 times 10 to the third volts gives a change in potential energy of negative 1.89 times 10 to the negative 2 joules. This negative result means the potential energy of the system has decreased. Consequently, an external agent would need to do positive work to move this third charge back out to infinity. Note that we ignore the constant potential energy between the first two charges because their separation distance does not change. To summarize our lecture, the electric field created by a point charge is a conservative field, which makes the electric potential difference between 2 points entirely independent of the path taken. The electric potential for a single point charge is calculated as the Coulomb constant times the charge divided by the distance. For multiple charges, the total potential is the algebraic sum of the individual potentials. The potential energy for a pair of charges depends on the product of the charges divided by their separation distance. Finally, a positive potential energy implies repulsion between charges, while a negative potential energy implies attraction. Before we conclude, please consider these review questions. First, think about why the mathematical expression for the electric potential of a point charge contains A1 divided by r distance dependence, while the magnitude of the electric field contains A1 divided by r squared dependence. Second, if you have a system of 3 charges arranged to form an equilateral triangle, how many individual terms must you sum to find the total electric potential energy of the entire system? You should be able to explain your answer based on the pairwise interaction rule we discussed earlier.